So, this is a nonlinear Schrodinger equation. Okay. So, you have seen this before. I am setting h bar as 1. Okay. So, I h bar d by dt psi is h bar squared Laplacian squared by 2 m, but I am set m is 0, m is 1 and h bar is 1. So, that is the linear part, but we have a nonlinear term here, nonlinear, no, mod psi square psi, and psi is a complex function. So, that is why we need to, I mean, in the real space itself my function is complex. Okay. So, what is the dispersion relation for the linear wave or linear system? Omega k is k squared, no. So, this I d by dt will give us minus omega, right, and that will give me the omega k is k squared, right, as straightforward, yes or no. So, you should put e to the power I k dot r minus omega t. If I substitute it here, then I get minus I omega, and there is I already sitting here. So, I squared will give you minus 1. So, this becomes omega, and minus Laplacian will give us k squared, right. So, this omega equal to k squared is the dispersion relation. Okay. And it is a dispersive wave because omega is not linear in k. So, I hope everybody understands that if omega is the linear function of k, then all the waves move with constant speed. So, if I take a packet, a Gaussian packet, then this will not spread. So, you should think that each component moves with constant speed, same speed, not constant, same speed. So, this packet is non-dispersive, that means this packet will, the width of the packet will not change with time. Okay. But we know in quantum mechanics, no, the width spreads because this omega is k squared. Okay. So, this is called dispersive waves, it disperses. The conservation laws, one is mod psi square dx, right, this is everybody knows, right, I mean one of this is a probability conservation, but we can derive this by Noether's theorem. I did this in the class by gauge invariance, okay, local gauge invariance. Second is conservation of total energy, which is not, this energy is different than h bar omega times mod psi square, mod psi k squared. Okay. So, this is for the linear part, well motivated by linear part, okay, I will say that. So, this is the total energy which is mod psi square plus lambda psi 4, which comes from which which symmetry property? What? Time translation, and space translation gives you linear momentum, which is the particle current. Okay. Now, in Fourier space we can rewrite that equation. So, this part psi cube, well it is not psi cube, is mod psi square psi. So, that becomes a convolution. So, we have psi k1, psi k2 and psi star k. So, psi star k is coming from one of the psi's here, psi star k3, alright. So, there is one complex conjugate in the right itself, right side. Now, I can write down the equation for the energy. So, what do? I multiply by psi star k and then add complex conjugate. By the way, I have taken the I from left to the to here. Okay. So, I just shifted I, is convenient for me. So, this I is coming from I h bar dt. So, I has been put there and add complex conjugate, you will get. So, this linear part will cancel, no, complex conjugate if I add I will get cancellations. So, we get for equation for the energy, if I write that, and please note that k1 plus k2 minus k3 is k because of this star. Is it clear to everyone? There should be minus k3 or k plus k3 is k1 plus k2. So, 2 in the left, 2 in the right, and the one with the star is going to be. So, if I multiply with psi star I will get psi from both sides, I will get psi star k. So, these two wave numbers are added and these two wave numbers, they are equal to the wave numbers for unstarred wave function. Now, particle density is mod psi k squared and energy is omega k mod psi k squared, and this is the equation which I can derive easily by multiplying by psi k star and adding complex conjugate. So, the right hand side has this quartic term, 4 terms like water waves, and this is the energy particle transfer function. I should not call it energy transfer because it changes the particle density at different wave numbers. Now, we can compute this Tn, and that is of importance. So, if I compute Tn, I just want to do the average first. Okay. So, I will get like this. Now, okay, I had forgot one part. This is the imaginary part, no? This because of this I sitting here, and when I add a complex conjugate, I will get a plus I. So, when I add, I get an imaginary part here. Okay. So, that imaginary part gives you something very interesting. So, if I do this, that is what I was water wave, I was a bit confused. If I do the to 0th order, so this is 0th order. So, quartic function function of 4 psi's will be product of a sum of products of 2 psi's. So, I get this plus different combination. How many combinations? 2 more, ABCD, ACBD, ADBC. Okay. And these are real, right? Here K2 is minus K1 when I do the integral, this is going to be energy and this is also energy. So, they are real functions. Imaginary part of real function is 0. So, 0th order I get 0. Okay. So, Tn is 0 to 0th order. Of course, I am assuming the size Gaussian, which is an assumption, but that is the starting point for most of the turbulence calculations. Okay. Without that, I mean, in Wilson theory also we assumed psi to be Gaussian for KPZ, for our hydrodynamic turbulence, all the time we assume psi to be Gaussian. Okay. So, we need to go to the next order. So, what do I do for the next order? I need to expand one of them using Green's function. So, I have this 4 psi's and I can take one of them and expand using Green's function. Okay, so, let us write down this stuff. So, psi k1, psi k2, psi k3 and psi star k. Okay. Let me just check which one I am doing is a Green's function. Okay, I am doing psi star, no psi 1, psi k1, psi k1. So, I expand this as a Green's function psi k1. So, standard stuff, no, we have the linear problem. What was linear thing? Theta psi equal to minus I k psi 1 omega k, sorry, not k, omega k psi k plus nonlinear term, which is minus I lambda integral and 3 psi's. So, I am going to write psi k1 here, my wave number of interest is k1, right, this one I am expanding. So, this will be omega k1 psi k1, and here I will get ds1, ds2, ds3, I write that 3 wave numbers, and I am going to write as psi s1, psi s2, psi star s3, and what is the condition for wave numbers? K1 equal to S1 plus S2 plus S3 minus S3, correct. So, this is the condition for the wave numbers. So, I am expanding this into the Green's function. So, this is what I have done, Green's function, and I got 3 psi's here and 3 psi's in the left, psi k2, psi k3 and psi star k. Okay. So, now 3 guys will come from the right, 3 guys will come from the left. There are many possibilities of putting them together. Okay. So, one possibility is that I put this is acting as psi star S3 or you can put psi star psi S2. This complex conjugate, well, I mean I can manage it, but psi S2, and this one is going as psi star S3, and this is psi S1. So, basically I am going to put them together, and there will be a wave number must match. Okay. So, so we will get 3 correlation functions or 3 particle density functions, right, correct. I mean this is particle density nk2, here I get nk3, and here I get nk, correct. So, these 3 nks will come, and that is what I got it here. I mean this is just algebra. I get n2, n3, nk, and by the way this is a time integral dt prime, and that gives you that this function should be delta function. This I did in the last class. So, you should see the video of the last class, and the delta function comes because of this dt prime integral, t going to infinity, t going to large value. Okay. So, this is for one of the terms, but we have more Feynman diagrams. What are the other Feynman diagrams? How many Feynman diagrams will I have? So, these I am doing only the psi k1. I should have a Feynman diagram from psi k2 like this, and like this. For each leg I can have Green's function expansion. So, there will be 4 terms, correct. Other term is Feynman diagram here 2, 3. Fourth one is Feynman diagram below like that. So, these are the 4 diagrams, and so we got 4 of these terms, and the sign I checked, this is what we get. Okay. And okay, so there is a lambda squared. Why lambda squared? Because one vortex is in the left and one vortex in the right, lambda. Okay. So, these t and k. Okay, this integral can be done mostly numerically, I would think. People have done analytically as well, and we can, well, this is rewritten as n1, n2, n3, n4, nk, okay, and divide by this. So, your choice, you can write like this or write like that. So, you see nk and n3 are coming with complex conjugates, remember in the first slide, and these are coming without complex conjugate, and this is the formula. Okay. So, this will give you the nonlinear Tn, nonlinear particle transfer function, and using this I can compute the flux. Okay. So, Sachin, you have to do all this work. So, summary is that we can evolve particle density and energy density function. So, this d by dt, it may not be in equilibrium. So, flux may not be constant, but well, that is a starting point for lot of calculations, analytical calculations, and derive energy spectrum, etc. Okay. So, I will end this part here. It's okay, everything is clear. So, basically we have quartic interaction. This is an example where we have 4 waves interactions. It's like 5, 4, 3. Definitely. So, but we can, I mean this derivation is not complex. Okay. So, I will do the last topic.